Hello, my name is Brian Brazel, and I'm here to give you a talk on counting with Prometheus. So to give you some background on who I am, I'm one of the 4 core developers of Prometheus, studied in Dublin, live in Dublin, worked at Google for a while, worked on many open source projects, and these days I'm the founder of Robust Perception, who does consulting and support for Prometheus, so if you're looking for that, talk to me afterwards. So Prometheus, if you aren't generally aware, just to give you some background, it's a metric-based time series database for white box monitoring. So solving the same sort of space that, say, Graphite would be, not the same sort of space that Elk would be. It supports labels, which are multi-dimensional tags. They're key-value pairs. There's no ordering on them. And it's got unified graphing and alerting. The architecture is service discovery figures out where everything is, all your pods or whatnot from Kubernetes or console. It then goes scrapes them, things like CAdvisor, Cassandra, JMX Exporter, your own applications, whatever. Stores the data locally, has rules and alerts, so it has a pretty complex query language called Prometheus, sends the alerts out to the alert manager, and then Grafana or other dashboarding solutions can get the data. There's something up in, I think, the 6-7 kilohertz range. I'm kind of hearing an echo. Is it? Yeah. No, I've got sensitive ears. Okay, so go on to the actual topic of our discussing counting. Counting is easy. We're all taught it in primary school, or as we're in Germany, Kindergarten. It's just 1, 2, 3. Nice and simple. The problem is that we're looking at monitoring events, or monitoring events interested in monitoring for a metric system. And we want to tell how many of those have happened inside the last 5 minutes. But the thing is that we're not seeing every single event because we're a metrics-based system, not a logs-based system. What we're doing is sampling every now and then, hey, what's going on? 20 seconds later, hey, what's going on? And the problem is sometimes there's data loss because there's a network interruption or the other end is slow or in the middle of doing GC or something. And we have this then partial view of sampled data, and how do we process then to answer the question of how many requests did I get inside the last 5 minutes? So I should say that there are basically 2 types of core metrics that you're going to come across in any monitoring system. There's also weirder stuff like hyperlog log. We're going to ignore those. You have the gauge. The gauge is just a snapshot of state. So canonically, your temperature or your memory usage is a snapshot. Who knows how it's actually moving, but it's just telling you right now, I am using 50 megabytes of RAM. They go up, they go down. Counters are the other base type, and well, we need to have a small explanation over the next 30 minutes or so of what a counter is. So the thing is, what we're trying to track is events. Events are something that happens, right? It might be a HTTP request, it might be a function call, it might be an exception, it could be anything. An event logging system like your Elk stack or anything or Graylog would have every single event, but not too much information about them because you'll run into bandwidth issues. A metrics-based system, whether that be Prometheus, Graphite, anything in that area, you need to aggregate those across time because we're just sampling. And that's where things get tricky. So there's a few different approaches that you will see if you look across all the different monitoring systems, like from IoT devices to switches to applications and to client libraries. The first and simplest one you will see in a lot of devices, particularly actual physical hardware devices, is the resetting count. It starts at 0. Every time there's an event of interest, it increments. And then however the data is transferred, whether it be push or pull, it sends the current count and resets to 0. And then, more events come in, it has the data, and then the data is transferred, it's reset to 0. And it keeps on working like that. Nice and simple. And here's how this works in normal operation. So this is showing 10 per second. And it comes along, and there's a big spike up to 50 per second for a 10-second period. So a nice simple example. And if you were to look at what's going on, it's fine. It captures this. It's a little laggy, that's fine. But it perfectly captures what's going on. And that's all fine. The problem is, though, that it's not quite perfect. So one thing, if a transfer fails, you've lost that data. And the thing is, though, that you might have to realize that this is not a random uncorrelated event. If you've just had a traffic spike, there is more chance that you are going to lose that data and miss that spike because, well, the network's busy. So there's a higher chance of packet loss that's correlated with the incident you're actually interested in. And also, if you have more than one place you're sending data, That doesn't work out too well because each of them's going to, or pulling in the data from it, they're going to each see half of the information. If you've got 3 places, or someone's just testing something in their workstation and using a pull model on that, that's not going to work out too well. So this is not generally a good approach, except in very specific circumstances. So if we presume that we lost a single point right here at the failure, we don't see it at all in our graph. The blue line is the true line, and we just see, yep, everything was perfect, it was normal, there was nothing out of the ordinary. You'd completely missed the fact that you had a big 5x spike in your data. So it has that disadvantage. The second approach, now this one is very popular. So DropWizard's Meter, for everyone familiar with the very popular Java library DropWizard, and it's porting into basically every other language. If anyone's using Go metrics in Go, that's DropWizard basically. It's a port. There's a few others in other languages as well. It works the same way as Unix load averages. So it's a bit of a way of saying, well, we take the current value, and we take 20% of it and 80% of the old value, and we add them together. And the next tick, we do the same thing again. So it takes the current value, adds it in, and smooths things from history. You do this regularly every 5, 10 seconds or whatnot, and there's a weighting factor deciding how much you care about old, how much you care about new. So DropWizard, for example, would evaluate that every 5 seconds. So that's how it works. And in normal operation, here's how it looks out. So, does that work? Mostly, yeah. Data comes along, it sees it, and because it's nominally averaging over 1 minute, it just displays this over time. And so it's actually reasonably accurate what you expect for a 1 minute average. And it just exponentially displays here. There are problems with the exponential moving average. The first is that because you're decaying exponentially, events are not considered equivalently. If you're transferring data every 10 seconds, and it's doing that tick every 5 seconds, data in the 5 seconds preceding your scrape matters more than the 5 seconds before it because of the decay. So that makes the math kind of tricky to figure out if you're not sampling it the same as the tick interval. And let's be honest, 5 seconds is quite frequent for data. And it also means because it's got built-in 1 minute, 5 minutes, and 15-minute weightings, if you want some other rate or want to get things faster or slower, you can't do that. And it's kind of resilient to missing a scrape. Like you can see that it will, it'll probably get here. You'll kind of have the information, but you're not going to see for the full spike. But it's not terrible, but it has issues. There's also a general issue we need to talk about. You're going to come across continuously in signal processing. You might have also noticed in my keynote, even with a diagram, is aliasing. So depending on exactly and precisely where you scrape, when you scrape, and when the data is coming from, you might see artifacts. Something called like the Quest-Shannon theorem, which states that you can only see features that are, half the frequency of what you're scraping at. And that even then the positive polymath to extract that frequency. So moving a second in either direction when you're evaluating something can make a massive difference in what you see. So who here has used Grafana and had a pile of, there's more to a different sentence, and had a graph, and hit refresh, and the shape of it completely changed. And then they refreshed and it changed again. That's all aliasing effects because basically you aren't scraping frequently enough to see the true nature of the graph. This happens all the time. And it's just a fact of life. And now, you probably shouldn't scrape more, you should switch to logs at that point because trying to do that sort of analysis of metrics, how fast do you need to scrape? Once every millisecond, nanosecond, microsecond? Switch to logs. You just need to be aware this is a thing that happens. And this also brings me to something else, a confusion that sometimes comes up from reuse. It's like, why don't you work like Graphite's summarize function? It gives me the right answer. Turns out, it doesn't. It gives you an answer which would appear to be correct via a naive analysis. So what it does is, let's say summarize in its simplest form, say, right, how many requests did I have inside the last hour? And it'll go and it'll look at data points in that last hour and add them up because they've already been converted to gauges. And there it is. The problem is that if the data point's at 13:02 and we're aligned on the hour, that 13:02 point, as let's say for 15 minutes, includes 2 minutes from the hour and 13 minutes from outside the hour. So it's not accurate because you're including all this data and you're missing all this data. So you're getting an aliasing issue there. So summarize is not accurate. because the data is extremely unlikely to be aligned. And you can imagine normally you're going to have things staggered because you want to spread load around, so it's always going to be inaccurate. This is not just me riffing on the summarize function. It is not possible for the metric space system to get this right. Prometheus also produces the wrong answer. It's merely a different wrong answer. I believe it's a better wrong answer, but just be aware, there's all trade-offs to be made here. Like, this is not an unreasonable way to do it in Graphite. But because of this issue, you're going to, the answer is just not right. If you want an accurate answer, use logs. But the thing is, both the previous solutions are kind of designed with the belief that the monitoring system on the other end is relatively dumb. Right? We've got something, if you've just got Graphite, which doesn't have, it's getting better over time, doesn't have that powerful a query language, or something like OpenTS2, which only very recently started to get a query language, only like in the release like 2 months ago, it actually started to get one. If you've got something that's basically just a dumb data store, you have to do all your smarts inside the client, whatever that is. If, however, you control both the client and the server and can put your smarts in the server, you can do some more interesting things. Because, like if you have a system where it's only a dumb database, having some inaccuracies is better than having nothing, right? That's just engineering. We have to make trade-offs. But we can do something a little better. So the third approach, is the approach taken by Prometheus Counters. And like the resetting counters, we have a counter that starts at 0 and is incremented in the exact same way. And it's regularly transferred, but it is never reset. It's only ever reset when the process restarts. And then the rate function takes us in and calculates how quickly it increases or decreases over time. Oh, increases. Only increases. Right. Counters don't decrease. So in normal operation, we'll see, now this is the correct answer mathematically because these examples purposely don't have aliasing because that's, another problem. But this is the 100% correct answer of what a 1 minute average looks like. So that's exactly what we want. That is the correct mathematical answer because everything's aligned perfectly. So it's resilient to failed transfers. You lose resolution, not data. So that's good. You can still see that, hey, there's more requests than usual. You just can't tell exactly when they happened. Multiple places can pull data from it or push data, whatever, no problems. And you can choose whatever time you want to average over that you want. Data is considered uniformly. It doesn't matter when it was like the first 5 seconds or the last 5 seconds of the 10-minute rate. It's all considered uniformly. And it's extremely easy to implement on the client side because you just have a counter that goes up. You need some mutexes and so on, but that's rather easy to implement. Now, if there is a failed transfer, let's say for whatever reason that this transfer around here fails, you'll just see the data, 10 seconds later. So that's, pretty good. We still see that, hey, there was an increase on average over this time period. We just see it slightly later because, the network didn't like that 5x spike. So that's going fairly well. So not perfect, but still pretty good. So then, looking at these ways, we'll talk about the rate function itself. Because some people are confused about some of the behaviors of the rate function, because it turns out the internals are complicated. And it took us a while. I think Bjorn did a lot of work on this, as did I, because the real world kicks in. Processes restart, it turns out. Yeah, scrapes get missed. Time periods, as I mentioned, because of aliasing, they rarely align perfectly. And, things start and stop. Maybe your project goes away or you deploy a new version. All these things happen and we need to deal with them in a way that is largely correct, or at least good enough, because we can't do it perfect because this is all metrics. If you want perfect, you need logs and to ignore general relativity. Entirely different topic. So the first problem we have is counter resets. Right? Counters can be reset to 0 and basically just normally only ever happens when a process restarts. So you imagine it's there, still sitting in the same port, same target, restarts, it's now a 0, because who wants to have to maintain straight across runs? Right? So because we know the counters only ever increase, what we can do is say, hey, that counter just went down. Therefore, it's reset. So if we see 0 to 10 to 5, well, we know that in total, well, it went from 10 to 5, so it was a counter reset there, so we had 10. So it went from 0 to 10, so it's a 10 of increase. Went to 10 to 5, so there's at least 5 of increase. So 15 total, and that's what we see. By contrast, if you're looking at Graphite or InfluxDB, the closest thing they have to the rate function is the non-negative derivative function. And what it would do is it would actually ignore that drop and just report the increase of 10. So we get a slightly better answer here. The second question of missed scrapes. Well, if we miss a scrape, it's fine. We've still got data points around it, and everything just works. But what happens just at the edge of the time period we're considering? That's more complicated. Because it's very rare that the rate will align perfectly when the scrapes are, especially once you have more than one target. And the fact that things are, in Prometheus at least, staggered on 1 millisecond intervals based on the hash of the target labels. So they're going to be spread all over that 5 minutes pretty evenly. And our timestamps are millisecond resolution, so have fun with that. So the thing is, if data points are near the edge, we need to extrapolate out to get the right answers. And this is where one of the big confusions around rates happens. Talking about increase, which is rate's brother. So rate returns per second results. Increase is just syntactic sugar around that. So if you have rate 5m, increase is the same as saying rate 5m multiplied by 300. That's only syntactic sugar, because people keep on asking us for this. Anyway, so let's say we have data, and at t equals 1, the data is 10. T equals 6, it's 12, and t equals 11, it's 13. So this has clearly gone up by 3 over this time period. And we want to look over from t equals 0 to t equals 15 and see what the rate is per second. Now, you could look at this and say, hey, over 10 seconds, it's gone up by 3. Therefore, hey, it's 3 over 10 seconds, and that the increase is 3. However, if you're looking over the 15 seconds, it's really over 4.5. So even though we've got all integers here, because we've extended from the 10 seconds that we have in data to the 15 seconds, we need to add an extra 5 seconds worth of data, which is 50% more, and we end up with 4.5. It is the correct result on average, because on average, if you look at it at different periods, it is 4.5. It's just because you thought, hey, it's 3, therefore it's an integer. No, it's a floating point number, and that's how integers end up as floats. I have a diagram for this one. So your data points are at 1 and 11, and you've got the other data point here. It's an average, so that's fine. And if we look at it literally, we just say, hey, that's 3. But the time period is further, so we have to extrapolate back to 9.7 and forward to 14.2, effectively. And we end up then with the 4.5 across that, rather than the 3 that would be here. Does that make sense? What's going on? Yeah, this is why that answer happens. And as well, time series are created and destroyed. If we always extrapolate it out to the edge, the problem is if a time series, let's say we're doing an increase over an hour, and a time series only exists for 5 minutes, we'd way overestimate if we always extrapolated it out to the edge, which would be a problem. So we need to detect that. So we basically get all the points, see how far they are apart from each other, average that, because that's good enough. And what we do is if the first point is within one interval plus some slack, we'll extrapolate. And on the other end, same thing, if the end is within 110% of the interval, we'll extrapolate. If it's not, it means the time series we think it started or stopped, and we'll just extrapolate 50% of the interval. The principle is if a time series disappeared, well, it could have disappeared, the process could have died any time from the scrape and when the next scrape should have been. On average, it disappears in the middle. So on average, we'll get the same result, and we do the same to start with something appearing. And one other thing we know, counters can't go negative because they start at 0 and only ever increase, so we don't extrapolate below 0. So here are all the examples. So this is a diagram. This took quite a while to produce. Looks very silly if you don't know what's going on, doesn't it? So we'll take, this is the simplest example here, this fella, the big long one. And what we're doing is that happens to start perfectly aligned. So it's simple. But at the end, because the next data point will be here outside the window, we extrapolate forward, and we calculate it based on that first point and that last point. With this one here, going back one, at the start, well, we don't extrapolate below 0, but it is within, an interval, so we extrapolate back to there. And at the end, well, it's not close enough, because the next point would be there, and that's within the window, because, it's here. So we just extrapolate 50%. And then this one here, we extrapolate at the end, and once again, to 50%. Because we're saying, on average, it probably disappeared halfway through. The slides will be online later. I always put my slides online later. Because, yeah, you need this text. But this is what's going on. This is just explaining all the cases of how we try to get this as right as possible, so we're correct mostly on average. And there is another issue, is that sometimes happens, which is time series that don't always exist. So we kind of presume that we'll see the time series, we'll see the 0, we'll see everything increasing from there. The problem is sometimes time series spring forth with a value of 1 and then keep that 1 forever. And if we look at that mathematically, well, it's okay, what's the increase in that? Well, there isn't an increase, it's flat. But if someone has just created this series and wants to say, yes, I want to track that 1 because that means an error I care about, well, we have no idea when that increase from 0 to 1 happened. Because from a time series database standpoint, for all we know, this application has been running for years. That increase happened a decade ago, and we just never saw it because Prometheus has only turned up. So we can't assume anything. We don't know. And the time series database wouldn't have this information. All it sees is a single time series with no context, because that's how it works. So the thing is that we are generally, in Prometheus, we're not trying to catch 100% of everything. So our answer is, well, we'll see the next increase. So you might want to have a different solution if you're trying to get 100% reliability, because Prometheus makes several trade-offs around availability versus precision and accuracy. So if you do care about this, logs. Logs are more accurate, especially if you get the type that are actually CP. Or make sure your counters are initialized when your process starts to 0, so we'll see that, because then the race is just down to that first scrape. Or just alert on the fact that it's 1, if you actually care about that. Because really, if you're indicating, hey, I'm in an error state, that's more engaged in the counter thing. There's another problem, and this is a general problem you'll see across most monitoring systems. Not all. Scientific ones tend to approach this differently. There's lag. You'll notice in all the diagrams we had of what was going on that there was lag of at least a scrape interval of seeing the spike, because all of them are looking back in time. Right? So if I've got a 5-minute rate at a given time, it's really a 5-minute average of the last 5 minutes. It's not centered on now. Similarly, when we're setting counters, we'll have the exact same issue. Exponential moving averages is much more complicated to explain, but the exact same thing is happening. It's always a lagging view. And that's the way it is. One of the reasons for this is that if we were looking at future data, that suddenly becomes very complicated, because it means if I was to evaluate a query and then new data comes in, the value of the query changes, that will be very hard to deal with, in your head. So one other thing to keep in mind is that rates are only really comparable if they're the same period. Like if you're comparing a 5-minute rate and a 10-minute rate and trying to divide them, that doesn't make sense statistically. So try to keep to 1 rate in your entire Prometheus. You'll thank me. The worst I ever came across was it 17 or 23 or something like that, rates inside a single file. Yeah, because someone had misunderstood how things work. Single rate inside an entire Prometheus, unless you know what you're doing. Maybe 2. 2 might be okay in special circumstances, as long as you never compare them. So we looked at how Prometheus does things. There are a few more complications in the client, because yes, it's a counter, it goes up. That sounds easy to implement. But you need to worry about the real world, which includes things like threading, because threading is a thing and has been for some decades. Concurrency handling, what you have available for you, varies by language. Mutexes, pretty much every language has mutexes, but they're also the slowest. So you're normally talking, about 100 nanoseconds for a mutex, except Python, which is 100 microseconds, or in fact, was it 500 microseconds? It's ridiculously slow in Python for reasons I'm not aware of. But then there's atomics. Atomics tend to be around the 10, 15 nanosecond range. And then the best one of all is if you can actually have per processor values, so you don't have to do cache coherency across the processors. So Java actually approximates this, so the Java client actually handles concurrency the best. But atomics are perfectly fine for average use, and some languages only have mutexes. Like the Go client is using atomics. The Ruby client doesn't actually have any concurrency handling because Ruby. Because it's presumed it's only single-threaded, so why would you need it? Yeah. So by comparison, if you look at how the drop wizard meter, it has to increment 4 numbers. So that's actually using atomics or the same double adder we have in the Java client. Anyway, the increment is quite efficient, but there's 4 of them because it has to do the total, and it's got the 1 minute, 5 minute, and 15 minute. And it also has to do the decay logic as well every 5 seconds. So it works out, the drop wizard meter, if you do the benchmarks, it's about 6 times slower than Prometheus counter, just to do your instrumentation. Now, this doesn't matter if you're doing it like 100 times a second, because who cares about an extra 80 or 100 nanoseconds a few times a second. Doesn't matter. But if you're starting to really instrument your code and have 100,000 or a million instrumentation events a second, which is normal, like it's not unusual for a single request to pass through like 100 counters when things are well instrumented. That can be more of a concern. I will mention though, the drop wizard counter, which is actually a gauge because it can go down, is as fast as a Prometheus counter because it's using the exact same double adder that the Java client uses. So that one's fine. It's just the meter which is doing all this exponential decaying windows that actually has performance implications. There is another implication which I wrote recently in a blog post, Prometheus labels in the child. So normally, if you are using the Python client or one of the others, you'll notice it's my metric, specify the labels, and then increment it. Right? It's not you don't specify the labels inside the increment call here. And this is because we have this thing returns what's called a child across the languages, and it's basically a map here, a concurrent hash map if you're using Java. And that map can actually be expensive. So it takes about 100 nanoseconds or so on Java. So if you think about that increment, that atomic increment is taking between 10 and 20 nanoseconds, depending on how contended it is. And then you add 100 nanoseconds just to find the thing you need to increment. That's pretty serious. Like that makes things 6 times slower. That's bad. So instead, if you can keep a pointer to this child, that's much faster. And this is why we do it this way. So someone, if they know in advance what label values they have, which is a fairly common thing, you can then just, cache that as a pointer directly to the child and increment it. And that's much faster. So if you are doing anything like that, that helps. Can't always do it, but that's handy. But if you're thinking, hey, I'll cache it inside a concurrent hash map, there's no point in doing that because this already is a concurrent hash map. You can't get more faster than that, at least in Java, and similarly in the other languages. There's a related anti-pattern you see sometimes, where people will create a map from metric names to metric objects. Don't do that. You know the name of your metric. Just keep a pointer. Because otherwise, you're once again going to have this hit. There are some just other best practices then to mention around counters. Use seconds for timing. Seconds are the standard. Everyone uses seconds, right? And then put that name inside the metric. There are other systems. You can see it sometimes with other things that they only support integers inside the database. So the developer has to choose, I'm going to use nanoseconds, microseconds, milliseconds, seconds, minutes, hours, days. I've seen all of these instrumented, sometimes inside the same binary. Like there was a time when Prometheus itself was using 4 different time units in its exposition. And this is Prometheus, no? We're meant to be better than that. This is silly. Just use seconds. We're using floating point numbers, so it'll automatically handle the exponent. Because the thing is that what unit you just have in your graphs is the display level problem that should be handled up at Grafana. It shouldn't be the concern of someone who's actually writing the code. It should just be use seconds, Grafana will take care of it. That's the way to approach this. In the same way that you don't choose your time zones down in your code, don't choose your units. That's a problem for the display layer, solve the display layer. Similarly, increase function, it's handy for display, but in your rules and in your exposition and so on, use rate for recording rules. Just so, once again, it's per second, nice, consistent, simple. And as I mentioned, increase is only syntactic sugar for rate. It's the exact same. There's no extra logic in there. It's just a multiplication to make your life a little easier. There is one other rate function called irate. It's not an angry function, although I think that's mentioned in the docs. In fact, I need to clean up the docs because that joke's getting a little stale. All it does is looks at the last 2 points in the range, right? And just says how fast they're increasing. So it's extremely responsive. You'll notice with rate, it's a 1-minute average. And the same, the explanation many moving windows are kind of a 1-minute average. But that means any spike or so on, it's averaged over a minute. Which can be handy if data is very spiky, because it turns out humans are really not good at dealing with spiky data, so you want to average it a bit. But if so there is irate if you want to see what's really going on, because it'll give you very up-to-date data of exactly what's going on. So if you're seeing lots of very brief spikes or microbursts and so on, you are going to want to have irate to see it. It's also handy if you don't actually know what the scrape interval is. But you need to be careful, because that's one of the reasons why it's used in all the console templates in Prometheus. We don't know what scrape interval you've used. You're probably using the default of 15, or maybe using a minute, or maybe you cut it down to a second because you like hammering your servers. So it's handy there. But you need to be careful you're not missing data. So irate itself In the perfect case, like you'll see this works exactly the same and gives us that same perfect answer we saw with the setting counters, which is good. And you'll notice the lag, though, as I mentioned, happens as well. When a failed transfer, like let's say this transfer here fails, we miss this, we'll still see a spike. It'll just be not quite as big. So you're still seeing a spike. It's resilient. It's not the perfect answer, but we have reasonably gracefully handled a failed scrape that happened because, well, there was an overload going on. So this brings us to the question, you have to be careful about missing data. The query range HTTP endpoint, so that's what Grafana is using. It basically says, hey, here's a start, here's an end. Evaluate this Prometheus expression at each of those data points. It's just it's a slightly optimized way of saying, run this query many, many times, 5 seconds apart, or 10 seconds apart, or 20 seconds apart. But if you have a 10-minute step, like you're saying is, right, run this over the last week every 10 minutes, with a 5-minute rate, you're missing half your data. Each of those requests is only looking at 5 minutes of data, and there's the other 5 minutes before it's missing. So you need to be careful. So you need to make sure your rate range is generally at least the size of your step. And in irate, you want your step to be no larger than your sample resolution. So it'll always have those 2 points, even if there's a failed transfer. So just keep that in mind. Otherwise, you're going to be missing data and not getting a true average because you're missing half of it. We'll also just mention the compound types. So we've got a summary. How do you track latency in Prometheus? 2 counters. Yay. You just count the total requests. You count the total latency. Get the rates of those, divide, and now you have average latency over any time period you like. Okay, the summary is basically just a convenient API for doing this because it's such a common use case. There's also quantiles, but quantiles calculated in the client are not aggregatable, and they tend to be slow because you need mutexes and lots of math. It can have some uses, it varies. The other one is the histogram. It also has the same count and sum that the summary has, but really it's for calculating quantiles in Prometheus. Because all it does is has counters, which are buckets, which indicates the histogram. You take the reach of all of those, which you can aggregate up then, and then you figure out, okay, so where's the 90th percentile here? So that works fine, but beware of cardinality explosion, because there's a general rule in Prometheus. You probably want to keep your cardinality below 10 on any instrumentation, and a histogram out of the box has the cardinality of 10. So you need to be careful. In general, with cardinality, there's maybe literally, for every Prometheus, you're allowed a handful of exceptions. So choose wisely where you're going to be. Because sometimes, hey, if you've got 12 types of logs you need to aggregate, well, there's your cardinality. That's life. But you should be very careful with instrumentation, particularly in libraries, not to blow out how much performance Prometheus can deal with, because monitoring is not free. Monitoring costs money and time and resources. And humans to have to fix, and go and retune everything. So summaries without quantiles are basically free. As soon as you start adding labels or quantiles or histograms, things start to get more expensive just because things are multiplying out. And so that's the main talk. The resources itself, you have the Prometheus website, user and dev mailing list. The source code is in functions.go, and there's also my own blog, which has some posts around this stuff in Prometheus generally. Cool. So any questions? We have 15 minutes for questions, or 14 minutes. Questions? Or are you still just ingesting all that? Everyone now understand why you can get non-integral answers with integral input to rate? Yeah. It's right on average. So any questions at all? Hand up. See? No one? Really no questions? Oh, there's a question there. What is it?
Are there kind of ideal kind of rates that you recommend? Like they're saying 1 second within time, but in terms of the actual rate to collect data, is there particular?
Okay, so the question is, are there recommended scrape intervals on Prometheus? It basically boils down to how much data and how accurate the data you need is. Because the way I see it, yes, you could scrape once a second and get really granular data, but you could also scrape once every 60 seconds and have 60 times the time series for basically the same performance cost. And which of those is more likely to help you in an emergency? Like having all your libraries instrumented or having this one metric that's awesome? And I would generally aim for breadth, like just having things liberally instrumented with no labels all through your code base, just so you can figure out roughly where is my problem. So I would generally, I've found personally, 1 minute is actually fine for the vast majority of things. And the only time you need down at the second range is when you're trying to debug, like for maybe literally a handful of metrics, when you're trying to debug, bursts of traffic that are in the seconds range. But breadth is generally best. A lot of people use like 15 seconds because that's the default, or 10 seconds. But you basically trade off, do I want a broader metrics or do I want the ones I have to be more granular? Cool. Any other questions? Put your hand up. Yep.
I have a general question about these metrics and math around. I feel like there's a lot of like patterns in your head. What should one do? Like an API, generic API, REST-based. What are the kinds of things we would measure if you don't know anything about the API? So like rates and like latency and whatever. I wonder if there is a place in the internet where people are currently collecting those, like, I know there is SRE book has some 5 golden rules of whatever if you want to measure whatever. I know them, but is there more on that? So
okay, so the question.
I don't want to say people do my work, but it's just like there should be some knowledge around how to use the query language in some basic use cases.
Okay, so is the question about query language or instrumentation?
I mean, it's collecting the metrics and also query language by pattern size. Are there some, or is it always specific to your use case?
So in relation to instrumentation, what's instrument was the first part of the question. If you look at the best practices on Prometheus.io, the instrumentation best practices answer that question, which is why I wrote them. The second question then is, are there common patterns around using things like summaries and so on? So the thing is, there's about 5 really, really common patterns in Prometheus. There's like taking your rate, there's aggregating that rate, there's using histogram quantile with rate and aggregation, and there's the summary doing the quantiles. They're very simple patterns. I'm not sure they're explicitly done. I'll put them in the blog eventually. They're on my to-do list. But those are the normal patterns. There's about 5 or 6 of them only that you need. And of them, to be honest, only the histogram and the summary require any thought. The rest of them is just take a rate and take a sum. But yeah, everything beyond that tends to be so weird that we basically need to ask a PromQL expert what you're doing, because you're doing complex stuff. Yeah, another question?
What's the difference between irate and delta, if I want to...
Okay, so the question is, what's the difference between irate and delta? Irate is for use with counters. It looks at the last 2. Rate that's much more responsive. Delta, by comparison, I propose removing from the language. Delta is for use with gauges, and it's the same as increase, but doesn't have the counter reset handling. The function you really want is called deriv, which will use a least squares analysis to figure out how fast a gauge is moving up and down. Because the problem with delta, because it's basically just using the first and last point and doing some extrapolation, is that it is extremely susceptible to outliers that happen to be at the start and end, which is a problem. Whereas if you're using least squares via deriv, it's not as dominated by any outliers around those points. So generally, don't use delta. But deriv then is for gauges, and irate, rate, and increase are for counters. That's our recommendation. There was a question there?
Yeah, the really basic question regarding rate. Do I need to put in the scrape interval into rate, or is that all done for me, or is that what the increase thing is?
Okay, so the question is, do I need to put the scrape interval into rate? The answer is no, because it has the data. It can work that out. But the range should cover at least 2 points, preferably 3 to cover a missing scrape. So normally, 2.5 times at least. Like if you had, let's say, a 10-second scrape interval, you probably want a 30-second rate at a minimum. Longer if you actually want to average stuff out.
But I always get the per second back.
Rate always returns per second, yes. Cool. Any other questions? Put your hand up. Anyone? Anyone hiding over here? The question? No, there was only about 4 of you I couldn't see. Okay, well, if that's it then, thank you very much.